Thus, the specific processes that can be probed with PET are virtually limitless, and radiotracers for new target molecules and processes are continuing to be synthesized. As of this writing, there are already dozens in clinical use and hundreds applied in research. At present, by far the most commonly used radiotracer in clinical PET scanning is fluorodeoxyglucose, also called 1,8-FFDG or fluodeoxyglucose, an analog of glucose that is labeled with fluorine 18. This radiotracer is used in essentially all scans for oncology and most scans in neurology, and thus makes up the large majority of all of the radiotracer, 95%, used in PET and PET-CT scanning. Due to the short half-lives of most positron-emitting radioisotopes, the radiotracers have traditionally been produced using a cyclotron in close proximity to the PET imaging facility. The half-life of fluorine 18 is long enough that radiotracers labeled with fluorine 18 can be manufactured commercially at off-site locations and shipped to imaging centers. Recently, rubidium-82 generators have become commercially available. 39 These contain strontium-82, which decays by electron capture to produce positron-emitting rubidium-82. Emission. Schema of a PET acquisition process. To conduct the scan, a short-lived radioactive tracer isotope is injected into the living subject, usually into blood circulation. Each tracer atom has been chemically incorporated into a biologically active molecule. There is a waiting period while the active molecule becomes concentrated in tissues of interest, then the subject is placed in the imaging scanner. The molecule most commonly used for this purpose is F18 labeled fluorodeoxyglucose, FDG, a sugar, for which the waiting period is typically an hour. During the scan, a record of tissue concentration is made as the tracer decays. As the radioisotope undergoes positron emission decay, also known as positive beta decay, it emits a positron, an antiparticle of the electron with opposite charge. The emitted positron travels in tissue for a short distance, typically less than 1 mm, but dependent on the isotope 40, during which time it loses kinetic energy, until it decelerates to a point where it can interact with an electron 41. The encounter annihilates both electron and positron, producing a pair of annihilation, gamma, photons moving in approximately opposite directions. These are detected when they reach a scintillator in the scanning device, creating a burst of light which is detected by photomultiplier tubes or silicon avalanche photodiodes, SIAPD. The technique depends on simultaneous or coincident detection of the pair of photons moving in approximately opposite directions. They would be exactly opposite in their center of mass frame, but the scanner has no way to know this, and so has a built-in slight direction error tolerance. Photons that do not arrive in temporal pairs, i.e. within a timing window of a few nanoseconds, are ignored. Localization of the positron annihilation event. The most significant fraction of electron-positron annihilations results in two 511 keV gamma photons being emitted at almost 180 degrees to each other. Hence, it is possible to localize their source along a straight line of coincidence, also called the line of response, or LOR. In practice, the LOR has a non-zero width as the emitted photons are not exactly 180 degrees apart. If the resolving time of the detectors is less than 500 picoseconds rather than about 10 nanoseconds, it is possible to localize the event to a segment of a chord, whose length is determined by the detector timing resolution. As the timing resolution improves, the signal-to-noise ratio, SNR, of the image will improve, requiring fewer events to achieve the same image quality. This technology is not yet common, but it is available on some new systems. 42. Image reconstruction. The raw data collected by a PET scanner are a list of coincidence events representing near simultaneous detection, typically, within a window of 6 to 12 nanoseconds of each other, of annihilation photons by a pair of detectors. Each coincidence event represents a line in space connecting the two detectors along which the positron emission occurred, i.e., the line of response, LOR. Analytical techniques, much like the reconstruction of computed tomography, CT, and single photon emission computed tomography, SPECT, data, are commonly used, although the data set collected in PET is much poorer than CT, so reconstruction techniques are more difficult. Coincidence events can be grouped into projection images, called sinograms. The sinograms are sorted by the angle of each view and tilt, for 3D images. The sinogram images are analogous to the projections captured by computed tomography, CT, scanners, and can be reconstructed in a similar way. The statistics of data thereby obtained are much worse than those obtained through transmission tomography. A normal PET data set has millions of counts for the whole acquisition, while the CT can reach a few billion counts. This contributes to PET images appearing noisier than CT. Two major sources of noise in PET are scatter, a detected pair of photons, at least one of which was deflected from its original path by interaction with matter in the field of view, leading to the pair being assigned to an incorrect lure, and random events, photons originating from two different annihilation events but incorrectly recorded as a coincidence pair because their arrival at their respective detectors occurred within a coincidence timing window. In practice, considerable pre-processing of the data is required. A correction for random coincidences, estimation and subtraction of scattered photons, detector dead time correction. After the detection of a photon, the detector must cool down again, and detector sensitivity correction, for both inherent detector sensitivity and changes in sensitivity due to angle of incidence. Filtered back projection, FBP, has been frequently used to reconstruct images from the projections. This algorithm has the advantage of being simple while having a low requirement for computing resources. Disadvantages are that shot noise in the raw data is prominent in the reconstructed images, and areas of high tracer uptake tend to form streaks across the image. Also, FBP treats the data deterministically. It does not account for the inherent randomness associated with PET data, thus requiring all the pre-reconstruction corrections described above. Statistical, likelihood-based approaches, statistical, likelihood-based 43-44 iterative expectation maximization algorithms such as the Shep-Barty algorithm 45 are now the preferred method of reconstruction. These algorithms compute an estimate of the likely distribution of annihilation events that led to the measured data, based on statistical principles. The advantage is a better noise profile and resistance to the streak artifacts common with FBP, but the disadvantage is higher computer resource requirements. A further advantage of statistical image reconstruction techniques is that the physical effects that would need to be pre-corrected for when using an analytical reconstruction algorithm, such as scattered photons, random coincidences, attenuation, and detector dead time, can be incorporated into the likelihood model being used in the reconstruction, allowing for additional noise reduction. Iterative reconstruction has also been shown to result in improvements in the resolution of the reconstructed images, since more sophisticated models of the scanner physics can be incorporated into the likelihood model than those used by analytical reconstruction methods, allowing for improved quantification of the radioactivity distribution 46. Research has shown that Bayesian methods that involve a Poisson likelihood function and an appropriate prior probability, e.g., a smoothing prior leading to total variation regularization or a Laplacian distribution leading to \displaystyle \L_1 based regularization in a wavelet or other domain, such as via ULF Grenander's sieve estimator 4748 or via Bayes penalty methods 4950 or via IJ Good's roughness method 5152 may yield superior performance to expectation. Maximization-based methods which involve a Poisson likelihood function but do not involve such a prior 53, 54, 55. Attenuation correction. Quantitative PET imaging requires attenuation correction 56. In these systems, attenuation correction is based on a transmission scan using 6/8 GE rotating rod source 57. Transmission scans directly measure attenuation values at 511 keV 58. Attenuation occurs when photons emitted by the radio tracer inside the body are absorbed by intervening tissue between the detector and the emission of the photon. As different lures must traverse different thicknesses of tissue, the photons are attenuated differentially. The result is that structures deep in the body are reconstructed as having falsely low tracer uptake. Contemporary scanners can estimate attenuation using integrated X-ray CT Thus, the specific processes that can be probed with PET are virtually limitless, and radio tracers for new target molecules and processes are continuing to be synthesized. As of this writing, there are already dozens in clinical use and hundreds applied in research. At present, by far the most commonly used radio tracer in clinical PET scanning is fluorodeoxyglucose, also called 1,8-FFDG or fluodeoxyglucose, an analog of glucose that is labeled with fluorine 18. This radio tracer is used in essentially all scans for oncology and most scans in neurology, and thus makes up the large majority of all of the radio tracer, 95%, used in PET and PET-CT scanning. Due to the short half-lives of most positron-emitting radioisotopes, the radio tracers have traditionally been produced using a cyclotron in close proximity to the PET imaging facility. The half-life